In this lesson, we're going to introduce the idea of momentum. So consider a hockey puck. We have it traveling along a surface at a velocity initial VI, and the hockey stick comes and exerts a force, average force, over a time delta t. So our intuition will tell us that this large impulsive force will cause the velocity of, if I have a larger force on the hockey puck, I'll have a larger final velocity of the puck. But up until now, we've only talked about force and time. Momentum is going to give us a formal relationship between the force, the time, the mass, and the velocity. So now we're going to take what we have learned about impulse and break it down to consider the impact on mass and velocity. So first, let's go back to Newton's laws, Newton's second law, which says that force is equal to mass times acceleration. So for the puck, the average acceleration equals the average force over the mass. And the average acceleration from when we did kinematics is related to velocity from average acceleration equals the change in velocity over the change in time. And the change in velocity is final velocity minus initial velocity. So now we're going to replace this part with we're going to replace average acceleration with Vf minus Vi over delta t, and we're going to rearrange the equation. So we put this up here, and we multiply both sides by mass, and then multiply both sides by delta t, and we end up with the average force times delta t equals mass times final velocity minus mass times initial velocity. Well, this part should look familiar. This is the equation for impulse. So what this tells us is that the impulse on an object equals the mass of that object times its final velocity minus the mass of that object times its initial velocity. So the left-hand side is the impulse, or J. The right-hand side is actually you can see it has final minus initial times mass. Well, mass times velocity is defined as momentum. mv is momentum. It's a quantity that's defined, and it's abbreviated by the letter p. So we don't use m to stand for momentum because we use m for mass. So now we have to pick another variable, and in physics we use the variable p for momentum. So an object's linear momentum, we're talking about in a straight line, is equal to its mass times velocity. Now you'll notice that momentum has an arrow over it. It is a vector, and it's in the same direction as the velocity vector. The variable is p, and the units are going to be mass is in kilograms and velocity is in meters per second. So the units for momentum are kilogram meters per second. Now we are later going to talk about something called angular momentum. This is momentum for an object that is rotating. Linear momentum is only applied when objects are going in a straight line. So momentum is a vector. It points in the same direction as the velocity. And so because of that, we can separate it into the x and y components. So sometimes you'll break it into x components. Momentum in the x direction is mass times velocity in the x direction, and momentum in the y direction equals mass times velocity in the y direction. Most of the problems we do in AP Physics 1, we're only going to be looking in one direction at a time. So it'll be momentum equals mass times velocity, and it'll only be the x components or only be the y components. But you could include both. So let's do a problem. This is just we're not going to have to do any calculations to solve it. We can just look at the equation to solve it. So remember that p equals mass times velocity. So which has a greater momentum? A truck traveling at 20 meters per second or a bike traveling at 20 meters per second? Well, you know their velocities are the same, but their masses are different. So the one with the greater momentum is the truck. Assuming it's more massive than the bike, the truck will have greater momentum. Which has greater momentum, a bike traveling at 20 meters per second or an identical bike traveling at 10 meters per second? Well, those bikes, since they're identical, have the same masses, so the only difference is their velocities. So the faster bike will have a greater momentum. Finally, which has a greater momentum, a large truck at rest or a bike traveling at 1 meter per second? Well, a bike at 1 meter per second has not a huge momentum, but it's more than the truck because the truck is 0. So the bike has the greater momentum. So now that we've looked at impulse and momentum, we can put them together in what's called the impulse-momentum theorem. And this comes from the equation that we did in this lesson that led to the definition of momentum. The average force times delta t equals m final velocity minus m initial velocity. This equation will lead to the impulse-momentum theorem, and it's just a rearrangement of this equation. It says that force times change in time equals the change in momentum. And the change in momentum is mass times final velocity minus mass times initial velocity. This equation is on your AP Physics 1 equation sheet. This is the only equation from the ones in this lesson that you will see, but this is the one that we'll be using. So the impulse-momentum theorem says the impulse given to an object is equal to the change in momentum of that object. So let's do a problem. We're looking at this from above. We're looking down on a ball. We have a ball that's traveling towards a wall. It's a mass 0.25 kilograms, rolling to the right at 1.3 meters per second. It's going to strike a ball and rebound to the left at 1.1 meters per second. So remember, we're looking down on it. So we're not going to look at y components, only x components. The first question is, what is the change in the ball's momentum? So we need to find its initial momentum and its final momentum, and then subtract final minus initial. So we can ignore momentum in the y direction because there's no velocity in the y direction. This is just rolling on a flat surface. In the x direction, the initial momentum, this is momentum in the x initial, equals the mass times the velocity in the x initially. So it's mass times 1.3 meters per second. So its initial momentum in the x direction is 0.33 kilogram meters per second. Now we can find the final momentum in the x direction, and it's mass times final velocity in the x direction, 0.25 kilograms, and make sure that your final velocity, because it's going to the left, that you put that as a negative 1.1 meters per second. So we get a final momentum of negative 0.28 kilogram meters per second. So our change in momentum is our final minus our initial. Our final is negative 0.28. Our initial is 0.33, but we're subtracting that. So we get a change in momentum of negative 0.61 kilogram meters per second.